Okay, so now that we've done the DSC run, and this is going to show us how to do the actual analysis using the software we have here. So some of this analysis you'll also be able to do with something like FIDIC that we've learned before, but I'm going to just walk you through here in case you can ever use this machine. I want you to be able to do those things. So the first thing is, after the run is complete, you'll notice that it goes to data analysis, and it should have your sample here. So we can kind of make that full screen, and then you can minimize it using the boxes up there. So that's what we have up right now. And so the very basic that you'd want to do is that you would want to make sure you can export the data to an ASCII format. So this is just going to be like a simple text or CSV format. And so you can include this other information. You definitely want to have data points. You can include calibration information as well. But you can see that it's automatically just going to make it a text file. So this is the text file that you should be able to read with Excel or some other plotting software. So that's the bare minimum that you want to make sure that you can do. So that's exporting the data, because this DSD you can't open and do anything useful on your own computer. I also want to show you some additional things that we can do with this software. The main thing is, you can look at, this is the whole curve. If you click this button, it zooms out and shows the whole curve. But we can also zoom in. So if I hit the zoom in, and then I can draw boxes around things that I want to look at. So if I click, I have to click up here first. See if I can get this right. There we go. So I can highlight, using boxes here, different areas that I would like to look at. So if I want to look at this peak here, I can zoom in. If I want to look at the area over here, I can zoom in as well. So you can use those, and if you ever want to go back, you can also just click full scale, and then I'll go back. But this allows you to change that up a little bit. All right. So if you just want to look at different features, so there's clearly a peak here, and so we'll want to look at how to deal with that. But also, you kind of have to zoom in. But if you zoom into this area down here, so if we go full scale, it might be hard to see. But the only other thing besides this peak, we notice that the background is very curved, and we might notice an initial blip here when the machine starts up. So if you ever see this blip at the very beginning of the testing, this is part of the instrument itself. So this is basically the heat up. This is when the machine is getting up to that temperature of 30 degrees Celsius. And so that is not anything to do with your sample. You'll notice if you look at multiple curves from different materials, you always see that initial blip at the beginning. And let me see if I can get a better view of it. Yeah, so you'll always see that little blip at the beginning. So, but otherwise, if we look at the other area, you might also, it's hard to see without having to zoom, but if you zoom in, you can also notice a little inflection in the curve, and it looks like it's at around 100 degrees. So let's, yeah, so right around here. So you notice that the curve is relatively smooth, and then there's this little step, and then it is relatively smooth on this side. So there's something happening here. And so those are the two things that we'll want to analyze. So what you've hopefully found from the background is that this type of step change is related to a change in heat capacity. And for polymers, this typically means it's a glass transition temperature. And so if I want to deal with that, I can go up here to calculate, and I can look at, I can either do what's called TG, or I can do step. And these will both give you the same information. So I'm actually going to choose step. So from this, I select the left limit, so you see the X here, and then the right limit, the X here. And what I'm going to do is I'm going to look for an inflection point. Oops, sorry about that. And so if I hit calculate, what you'll see is that lines will form. And so basically this line here is modeling the curvature before the inflection. So if I kind of take the line and do something like this. And then I also want to adjust the other, right? Because it looks like if I model the line above, so up here, I'm trying to model both the curves above and below. So I'll use those. Right, so I'll do something like that, and then I'll calculate. Okay, so let's try this again. So I'm going to go to calculate, and I'm going to use the TG function to try to get this TG. It's got the baseline's endpoints. If I hit calculate, it's again going to ask me for these tangents, and again I can't have them cross, so I'm going to get them as close as I can to the curvature while still not crossing, and so that's what I have here. And if I hit calculate, you'll see that it picks the TG as this point here, so where the inflection is, and that's at 98.7 degrees Celsius. And it also gives you the change in the heat capacity that occurs. So this is also something that we can use in these calculations. Okay, so that's how we can do the heat capacity. We can also get information about this peak. So as you kind of see from the scale here, this says heat flow and it says endo is up. So this is an up peak, a positive peak. And so this is endothermic. And so if we calculate, and we can just do it simply by looking at the peak area, and we can select our endpoints. So I'll pick them here. So basically where the endpoints of we're going to analyze. So you want to make sure it's on either side of the peak. So it kind of encompasses everything that we have there. All right, so let's do that. So we're going to use a standard baseline. So this is basically going to be a linear line. There's more complicated ways you can do it, but a line should work for the most part. And so this is what you're going to get when you hit calculate. So it fits the black line, that's the background, and you see it represents pretty well what the red line, what our baseline curve looks like. It picks the peak. So this is kind of the center for your data here, and so that's 255.7 on this one, and it also gives you some area information in millijoules, but it also gives you it in terms of grams for the weight that you added. So this is why we want to make sure we have a proper weight. And so for this endothermic peak, it tells us that we have a change in the enthalpy, delta H, of 40.7 joules per gram. And it also tells us this endothermic event is centered at 255.7 degrees. And so if you think about all the types of endothermic events that we can have with a polymer, this will be a critical thermal event that happens in these materials. And so you know the temperature that it happens at, and you also know the enthalpies, and this will be useful when you identify the polymer. You can go back and calculate enthalpies, and these values should correspond to what you get for that material, and it'll help you look at things like percent crystallinity as well. So these are kind of the simple analysis tools that we can do with the software. So we can get step changes and we can get peaks. If we had more peaks, we could do the same thing to those, and we can export this data, take a screenshot, and get all of this data. You can also do the same peak fitting that you've done here. You can do that in FIDIC as well, so feel free to use those techniques as well to get some of this peak information.